Hey everyone, welcome to This Explainer. Today we're heading out to the darkest edge of reality. You know, that place where our fundamental understanding of the universe is supposed to shatter. For, well, nearly a century now, we've been told that right at the heart of a black hole lies a place where the math of the cosmos simply gives up and breaks down. Just infinite darkness and infinite confusion. But what if the math isn't actually broken at all? What if we've just been kind of reading the universe's geometry the wrong way? So I want you to picture the classic singularity. General relativity tells us that matter just crushes down into this unimaginable point of infinite density, a spot where gravity goes off the charts, where space and time literally lose their meaning, and the laws of physics just, well, they stop. It's a pretty terrifying concept, right? This idea that nature actually has a physical error message built into it, like an ultimate dead end where everything we know is just destroyed. Okay, let's dive into this, because this is where mode identity theory comes in, and it offers a profound solution that completely changes the game. It proposes that the universe isn't actually failing at the center of a black hole. Instead, as the theory puts it, the wave persists, the topology holds, the observer goes silent. Think about that. We're shifting away from this old paradigm of violent destruction, moving towards one of, honestly, elegant topological persistence. Act 1. The myth of the singularity. To really wrap our heads around this, we basically have to completely reset our mental models. General relativity gives us that classic singularity we talked about, that crushing point of infinite density where information is violently destroyed. But mode identity theory, it replaces that infinitely dense dot with what it calls a double zero. This isn't a crushing point, it's an elegant geometric node where both phase and scale simply collapse. And the absolute most crucial distinction here, information isn't destroyed at all. It's merely unsampled. So you might be wondering, why did general relativity get it so wrong? Well, it's because it's an incomplete equation sitting right at an interface. In mode identity theory, general relativity basically sits between the temporal edge of the universe and its spatial surface. So when it hits the black hole horizon, the math breaks, because it's literally being squeezed from both sides, by a collapsing scale on one end and a vanishing mode on the other. The universe doesn't actually end there. It's just that the specific equation we were using to measure it, well, it runs out of runway. Act 2. Reimagining the horizon. And this brilliantly illustrates our next point. If the singularity is a myth, what actually forms that boundary? Enter the topological silent node. I want you to think of the universe as a giant standing wave. The horizon of a black hole isn't a physical wall. It's simply a point where the spatial mode reaches a geometric node and observation ceases. It's exactly like hitting a node on a vibrating guitar string. Let's break down this guitar string analogy for a second, because it's literally the key to everything. The universe doesn't just snap its strings. The string itself is still perfectly intact, right? And the wave continues to pass right through that node, but the physical displacement at that exact specific microscopic point is zero. You simply cannot read the wave there. Information isn't burned up in some theoretical firewall, it just becomes completely invisible to the observer. Act 3. The double zero and the leak. Now, what's really interesting about this slide is how it breaks down the three massive factors driving this double zero event. First up, theta approaches zero. This means the actual phase position hits the boundary of the domain, simply because the sheer amount of enclosed wave content pushes it to the absolute limit. Second, and this is a direct consequence of hitting that node, the sampling amplitude C vanishes. You just can't observe it anymore. And third, the independent partner in all this, omega h approaches zero. This means the local scale hierarchy completely collapses. And that third point, the scale collapse, that is truly mind-bending. The phase gradient length shrinks down to absolutely nothing. This means the distinction between the unimaginably tiny Planck scale and the massive cosmic scale, they merge into one. When this local hierarchy collapses to zero, the very concepts of a surface or an edge lose all operational meaning. As the source text puts it so perfectly, the fundamental filing system of the universe is just gone. But, and this is a big but, remember, the wave itself doesn't disappear. While the observational value vanishes quadratically at this node, the math tells us something incredible actually survives. The leading non-vanishing order, which is essentially the curvature of the wave at this exact node, is exactly 4 pi squared. So the zero acts like a filter, and this highly specific geometric curvature is what manages to survive right there at the boundary. So the crucial point is how this completely rewrites our understanding of black hole evaporation. Historically,
We've thought of Hawking radiation as these kind of magical pairs of particles popping into existence near the event horizon. But mode identity theory redefines it completely. It says Hawking radiation is simply the residual sampling at that first non-vanishing order of the double zero we just talked about. Basically, it's a topological wave leak seeping right through the boundary. And this leak triggers a genuinely fascinating mechanical runaway process. See, the gradient of that sampling amplitude controls exactly how much of the wave leaks out. As energy leaks, the enclosed wave content inside the black hole obviously decreases. This causes the zero boundary to contract. And when it contracts, the gradient steepens even further, which lets even more mode structure leak out into the universe. It's an elegant loop, and it perfectly explains why smaller black holes radiate and evaporate way faster than supermassive ones.
Act 4, information is never lost. Which brings us to the profound climax of this entire theory, resolving arguably the biggest crisis in modern physics. For decades, physicists have been proposing these wild new physics ideas to save information from being destroyed in a black hole, things like crazy walls of fire, complex complementarity, or bizarre remnants. But here's the stark reality of the double zero. You cannot perturb your way out of a topological node. The singularity is double zeroed. This means the information paradox is completely solved, purely by the existing shape and topology of the universe. Absolutely no new physics required. Let's move to the next point and see how this builds, because it all leads to one ultimate takeaway. Information is unsampled, not destroyed. The wave of reality doesn't break at the edge of the dark. It simply slips past the limits of our observational grid. The indestructible nature of reality holds firm, even in the most extreme, mind-boggling gravitational sinkholes in the cosmos. Which leaves us with a pretty staggering realization. If mode identity theory is correct, and the foundational wave of the universe persists silently and perfectly, even when we are completely unable to observe it, what else is playing out there in the dark? What other magnificent structures are hidden right in front of us, just waiting in the unsampled silence? It's a question that redefines everything we thought we knew about the night sky. Thank you so much for joining me for this explainer, and hey, keep questioning the dark.